Yeah, hi all. So, in the beginning, Nilima mentioned in mornings that there were few people here who attended the first PNLD. So, I was one of them. I attended first PNLD in 2004 as a graduate student, and that was the first PNLD, and that was also like my first big international conference in nonlinear dynamics. So, let me start with my talk, which is about couple dynamics on higher order interactions. So today I'm going to focus more on the higher order interaction, and I'm going to give you some glimpse about this very fascinating area of research which last 2-3 years this network science has witnessed. So let me see if it is working. Yes, so I will present this excitement of higher order interaction using this Kuramoto oscillator model. I'll take this adaptation because this is my area of the work. Like I will also give some of my results, recent results, which is about adaptation. And this thing would be, entire thing would be about beyond pairwise interactions. This is higher order interactions. And this work I have done with two very talented young collaborator of mine, Priyanka and Ayushi, who are in audience, who are the PhD student in my lab. So let me start with what is higher order interactions. So for networks, so let me explain it slowly. So networks capture only pairwise interaction, like let me call it one simplex. So mathematically it is one simplex. Now this triangle, this is two simplex, then tetrahedral, you have three simplex, and so on. And it has been realized that functions of a range of real world complex systems, they are governed by higher order interactions. And let me first give you one very intuitive examples, and then I will have a list of the examples which have evidence of higher order interactions. So one very intuitive example is scientific collaboration network. For example, A, B, C, there are three authors who have written paper together, and they don't have any publication which is A and B have worked upon. So they have never written a paper in the pairwise. So in that system, if you take network theory, traditional network theory, it will talk about the pairwise interaction, but no, the pairwise interaction in that particular example does not exist, because the outcome of the project, the paper, that is the collective, that is the three nodes interaction. So that is one example, co-authored by D authors make an hyperase, which is grouping them. So this is one of the example of higher order interactions. And then you have several examples. So one which I also like a lot, that is from Danielle Bassett group, where she has shown that you have this enclosed cavity in the brain, and this enclosed cavity, which is like the triangles in the brain, play a very important role in information transmission. And similarly in ecological system, 3 or more species, they can jointly compete for the food. Then you have multi-component interactions in the brain, protein interactions. A lot of work recently have been done which try to emphasize the existence of such kind of higher order interaction, and that gave a lot of a drive for this data science. Given the data, how to infer the higher order interactions, because you have Pearson product correlation for the pairwise. So how to detect higher order correlation? So entire this data science, and this Battiston group actually has written the first very nice review article in 2020, which is mostly based on, his group is entire this data driven kind of thing. And in last 3 years, you can see there are 2 physics report article, and this physics report, I am also one of the author here, and you can see the similar title, but so much development has been done in last 3 years that demanded another physics report. So this is the drive in the higher order interactions. And now let me come to the example which I am going to present today, and to share that what new phenomena this higher order interactions can bring up. So I'll take very simple this phase oscillator model, one dimensional simple phase Kuramoto oscillator model, which we know that in absence of any interaction, the oscillator will keep on moving in coherent fashion unless and until you have identical oscillators starting with the same initial conditions. They will be all keep on moving in the steady state. And then if you have weak coupling, then there are evidences of chaos as well, which I am not going to touch about. I am today going to talk about this synchronization. I am going to present the example of synchronization to demonstrate that what higher order interaction does here. Right now there is no higher order interaction, so let me spend some time here. So you have this chromata oscillator with theta as a phase, ith chromata oscillator, d theta by dt, omega I is the intrinsic frequency, and this is the pairwise interaction which Kuromota proposed in 1980s. So, and here very simple model where all the oscillator are interacting with all the oscillators. So summation here is going from j is equal to 1 to n. K is the pairwise coupling strength and n is simply normalization. And it was shown that as coupling strength is strong enough, you get synchronization, means theta I is equal to theta j for all theta I j for all time t greater than some initial transient. And you have one order parameter which is for the measure of synchronization. So here you can see this is the complex order parameter, r is the real part, psi is the mean phase of the oscillator, and with this equation you can immediately see that if oscillators are homogeneously distributed in a circle, then r would be 0, and if oscillators are synchronized, then this scalar part of this order parameter will be equal to 1. So r captures, or r is the measure of synchronization in the oscillator, and it was landmark work by Kuromota which showed that as you keep on increasing k, in the beginning there would be this r is equal to 0 remains the stable fixed point, and as it reaches to a critical coupling strength Kc, it witnesses a supercritical bifurcation, and r is equal to 0 becomes unstable branch, and you have one stable of course in the positive direction, and there you will have negative direction which is inadmissible because r has to be physically positive quantity, and you get this second order phase transition, supercritical phase transition, and so and to the synchronization. As you keep on increasing, then it will become synchronized, r will be equal to 1, and there is a very nice article by Stogatz which I enjoyed a lot reading from Kuromota Crawford, showing that why this simple oscillator is so interesting and exciting and what new one can learn. So this is all with the pairwise, and of course this simple Kuromota oscillator gave many fascinating things, like you include here phase here, then make it more generalized, then chimera, explosive synchronization, all. And what I am going to do today, that is I am bringing this phase oscillator, and then I am going to bring this higher order interaction. And I will show that how this higher order interaction changes the dynamics. Okay, so this is one model, this is not my work, I will show my work which is, I promised it was on adaptation. This is just to introduce you that what higher order interaction can bring. So now you have, instead of, you can see here pairwise, what I have taken this triangle interactions. So you have j, k and I. So instead of theta j minus theta I, which was in pairwise, now in sinusoidal term you have 3 terms, okay, and here summation is also running over all j and k. This is the coupling strength, and this is some normalization which you can ignore for time being. So you have intrinsic frequency, same as in the previous case, but instead of pairwise, now you have triangle interaction. Any guess what you can witness here? So now we don't have pairwise interaction. Okay, we have only higher order. Right now triangle, so higher order I am using right now whenever I am talking about triangle, but higher order also includes triangle, tetrahedral and so on. So what happens, this green line that shows in the forward direction, it means you start with the random initial condition and then you run. So you can see that r is equal to 0, that remains a stable solution for all lambda values. So you don't get any synchronization in the forward direction, and I will show entire mathematics also behind that, analytical calculation also when I will present my example. But you don't have forward direction synchronization because r is equal to 0 remains the stable solution for your odd and tension manifold, which I will show you. In the forward direction you don't have any synchronization because of the frustration which is being caused because of this triangle thing. So pairwise was supporting the synchronization, whereas triangle, it is inducing some kind of frustration in the system, and your synchronization is gone. But you have one stable solution in the backward direction. It means if you start with r is equal to 1.
The Pramana paper, the ACN resolution.
Okay, so if you start with r is equal to 1, right now also ignore these quantities, but you start with r is equal to 1, then you are there with r is equal to 1 for certain coupling strength, and you have explosive desynchronization. You have your saddle node bifurcation, and that is referred as explosive desynchronization. So you get back to the r is equal to 0 state through a saddle node kind of bifurcation. So you don't have any synchronization in the forward direction. Eta is the initial coupling strength, which I said as you can ignore because I don't want to explain it, but this is, eta is the number of oscillator. So if a 100% oscillator is the same coupling strength, eta is equal to 1, 90% oscillators, then eta is equal to 0.9. So it was, I don't want to go into details now, but maybe we can talk this thing later. So, but the take message here is that in the reverse direction, you have this explosive desynchronization, okay? And so no forward direction synchronization, and instead you have explosive desynchronization, which was put forward by Skardar and Arenas in 2019. And we have also shown recently that if we evolve this thing using Hebbian learning, which is also, I am not going to explain in details, I am just mentioning, then also we get such kind of thing, but in the cluster domain. Maybe time permits the end, I will explain that. So now the natural question is, now if we take pairwise and higher order all. So right now this is pairwise, and now this is triangle, and this is tetrahedral, and you can keep on going that. But suppose now let us only focus on the pairwise and triangle. So pairwise we knew we have forward direction supercritical bifurcation. When we have triangle, we didn't have any forward direction synchronization, only in the reverse direction. Now you merge both. What you are expecting. So when we merge both, let us make K2 and K3 fixed. It means we are fixing the frustration which is there in the system, and we are only increasing the supporting force. And as I think some of you might have expected that we get forward direction and reverse direction both. Since the frustration is at the bay, we are keeping the frustration in control. Frustration here I am saying in terms of this triangle interaction. So K2 and K3 we are fixing, and we are only increasing K1 here. So you can see R is equal to 0, that remains a stable solution. It becomes unstable, but instead of supercritical bifurcation, now you have subcritical bifurcation. So this trajectory, this R is equal to 0 becomes unstable, and trajectory jumps to the far away attractor, and we have other unstable branches actually here, which in analytics actually we witness, and I'll also show later when I present my example that you have unstable branches here. So in the forward direction you get subcritical bifurcation, reverse direction you get, so it's this entire hysteresis which you find, and that is when you have this both things coming together. And this is the entire stable and unstable branches, which let me explain a bit of this part. So here you can see that you start this pairwise coupling strength when there was no higher order interaction. It means K2 plus K3 was 0. You get this supercritical bifurcation, the second order smooth phase transition. As you keep on increasing this K2 plus K3, you can see that you start getting after a critical. So after a critical K2 plus K3 is achieved, you get from supercritical to subcritical bifurcation, and this is unstable branch. This dotted line in the unstable branch, and I will show this Ott and Tinson methodology later, where one can actually get everything, the entire phase space one can plot. So here you have saddle node bifurcation and conversion from supercritical to subcritical. And one interesting thing which I would like to just note, and Vasundhara has a poster on this idea, on this topic, which is that you can see that you can get synchronization even in the negative coupling regime. So contrarian that synchronize, and she will show for the multi-layer networks where the entire hysteresis and everything that is in the negative regime, that is in the poster. And why one should be interested in the first order transition to synchronization? So there are several examples: chronic pain in brain, cascading failure of power grids, jamming of internet, brain disorders such as seizure, Parkinson, and this anesthetic-induced transition to unconsciousness. So all these things have been shown or discussed or debated to be attributed because of this sudden change in your activities by the fine-tuning of the parameters. So one should be really interested about this first order. And I want to show you some movie here that how this second order phase transition and first order phase transition, they work. So let me show you this movie. So this is now left hand side is second order phase transition. So you have this green dots that are the oscillators, and this red dot, that is the R, which is the length of this red dot, that will show you the order parameter, and then green dots are nothing but the oscillators. So as you keep on increasing the coupling strength, you can see after certain coupling strength, these oscillators will start coming closer. Slowly R is increasing, you can see R is increasing, and after certain like as keep on increasing the coupling strength, all oscillator will start moving with in the synchronization. That was the slow, smooth movement to the second order transition. And you will realize this contrast if I will show you this first order one. Again the same thing, but now the first order you can see that I'm increasing the coupling strength and nothing is happening, and suddenly you will have this jump to the synchronization. So this is just some example, some video just to emphasize upon. Okay. Now what I am going to show you, this is higher order interaction plus adaptation. And what adaptation? So without adaptation, this was the first few slides I have shown that this is the pairwise interaction, you get second order transition. Now if I introduce this adaptation, now here how I am introducing, there can be several ways one can introduce the adaptation, and here I am introducing this adaptation to the global this feedback kind of thing. So you have R, which is the measure of synchronization, and here I am multiplying R, and in the next slide I have few examples where this kind of adaptation that makes sense, but you can have several different adaptation like Hebbian learning, etc. And this is one type of adaptation which people have investigated with the pairwise interactions, and they have shown that as soon as you put the adaptation here, like you multiply R, and this is the some alpha, some parameter which is there with the R, and depending upon this alpha actually you can get this first order transition to synchronization. So when you didn't have adaptation, you were getting second order. As soon as you put the adaptation, you get the first order. So that is the existing results which is there with the pairwise interactions. And such kind of adaptation, one can think that in the brain you have connection among neurons which can adapt based on the synchronous activity. Another example is the clapping. When you are in auditorium, you are clapping, and then your coupling strength, so you keep on getting more and more synchronized because of the sound which you are hearing. So sound here, somehow this is acting of some kind of this feedback. So there are few examples which I have listed here, and then of course you have Hebbian learning rule which says this is another form of adaptation, that those which are connected, they keep on becoming more and more stronger if synchronization between those entities they have. So there are several forms of adaptation, and I am taking here the global adaptation, which is something like that. So this is second order. Now if I introduce without adaptation higher order, you get first order transition to synchronization. Now what I am doing, I am introducing this adaptation here, R, which I am multiplying here with K2, and similarly I have actually, I apologize here, there should be R to power alpha as well. I think it will come later, but R to power alpha would also be here, okay. And now you can see that you get a very different kind of emerging behavior. So right now for beta is equal to 0, no adaptation, you can see that you have first order transition to synchronization, this red dot, and then you have this hysteresis thing. As you keep on increasing beta, you get very counterintuitive result, and I will show that why these results are coming. You get the second order transition to synchronization. It means pairwise term is dominating. An intermediate state, you get tiered synchronization. So here you can see, if you follow me here with my this pointer, you can see that you have here first some kind of supercritical bifurcation, very continuous kind of things. And then you have here serial node bifurcation, and you get a jump. So this is something known as tiered synchronization. It tries to follow the behavior of pairwise interaction, but this higher order become dominant here because of you have this adaptation here, and then you get this first order transition to synchronization. So you have restoration of second order because of this adaptation, okay, so you don't have first order anymore. And then you have tiered synchronization, and this got published recently in Chaos as a fast-track article, and let me show that why it is coming. And this is very beautiful, this Ott and Tenson approach, which was introduced, proposed by Ott and Tenson, and it got published in Chaos in 2008. That provides a very beautiful way of dimension reduction. So now you can see here you have n oscillators which are interacting. I is going for 1 to n. So this n oscillator, what he proposed, which I will show that one answers, which reduces the entire n dimension into one dimension. So what is the first thing? He just wrote down, like this is the standard mean field kind of things here. So I have written the entire thing in the thermodynamic limit in terms of mean field, where all the oscillators, instead of seeing the other oscillator, they are only experiencing a mean field, the psi1 and r1. And r1 is the order parameter which is for the global synchronization, and r2 is the, which I missed actually writing here, I think it will come maybe later, I missed. This is for the cluster synchronization. So r2 is the, instead of e to power I theta in the summation, you put e to power 2 I theta when you define this r1 and r2. So you have this, so all the oscillators, instead of seeing other interactions from the other oscillators, they are only seeing the mean field, okay. So they are seeing the mean field through this mean phase psi1 and psi2, and of course this r1 and r2. So this is the mean field thing, the first, but still it's n-dimensional. Still I have not done any dimension reduction. Then you write down this continuity equation, because number of oscillators, they are preserved in time. And then after writing down the continuity equation, you make the Fourier expansion of this density function. And now here the trick comes from the Ott and Tenson. So here Fourier series expansion, you can see there are n components, with n going from minus infinity to plus infinity. And his answers, which was that instead of writing down infinite Fourier modes, he defined, this was answers that he wrote down a function v, and to the power. So instead of this modes, he has the power of n, so you have only one variables, and of course this answers work under certain conditions, but in this case it works very nicely, that this has to be less than 1, and there are certain assumption there, but it works here. And once you substitute it here, now you can quickly see this is a very simple algebra. The entire thing collapses. You just put it back here in the continuity equation, put it back, and then compare the left and right hand side, the component corresponding to e to power I theta, e to power 2 I theta, and all those collapse into this continuity, this single variable equation, which is for v, okay. So now you can see here everything we know, this omega is given to us, which is the intrinsic frequency of oscillators. And this is the self-consistent equation, because still you have R1, Z1 is the complex order parameter, R1 is the real part, and Z2 is the complex order parameter for the cluster synchronization, where you take e to power 2 I theta to e to power 2 I theta. So now you can see the self-consistent equation, but for particular frequency distribution, intrinsic frequency distribution, one can actually show that V this collapses to the order parameter. So you do the complex integration by taking, for the order parameter R, you write down into the continuity in the thermodynamic limit, substitute back everything there, and if you take this intrinsic frequency distribution by the Lorentzian distribution, then integration, the complex integration becomes quite easy, and then finally you get everything in terms of this order parameter. So now you can see that entire n-dimensional equation, due to this Ott and Tenson one answers, which I have taken in the previous slide, you have one-dimensional differential equation for the order parameter. So now you can do the entire stability analysis, put R dot is equal to 0, you get all the fixed point of the system, then you do all this linear perturbation, this Jacobian analysis, and then you can find out whether those solutions are stable, unstable, what kind of bifurcation. So you know everything after you have calculated this one-dimensional differential equation. And now here you can see that for small k2 and large beta, pairwise is dominating. So when you have small k2, of course, pairwise will dominate because k2 is the higher order interaction. But for large beta, because R is always less than 1, so as you are having higher beta value, you will have the contribution in the second term that will become smaller in your this coupled differential equation, and then you have this K1 that will dominate, and that is the reason that as you are keep on increasing beta, you restore this second order transition because your K1 term that will dominate. So R is equal to 0 is stable for K1 less than 2, and after that, of course, it becomes unstable, and then you have subcritical and supercritical bifurcations. So, and then we have this entire phase diagram here that when we get second order, because this is now very easy to do the entire phase analysis, you can plot second order when we get tiered and when we get first order. So you have very beautiful different design which appears in the same equation because you have, because of this higher order, you have much richer dynamics which is possible. With that, let me ask how much time I have. How much time I have? 10 minutes. Okay, so then I quickly then summarize this thing. So this is another result where I have adaptation which is taken in different manner with the Hebbian learning rule, and I am just rushing it fast here, and I just want to emphasize on one slide, no adaptation, we get global synchronization. So here instead of taking adaptation here with the R, I have taken adaptation which is there in the interaction, and that is motivated by the Hebbian learning rule. And if I take the adaptation which is motivated by here, Hebbian learning rule, then instead of global synchronization, I get cluster synchronization. And with this, I think I don't want to confuse you all with many different results, and hence let me proceed to the conclusion because I would like to have some questions. So adaptation in pairwise and higher order, that independently leads to the first order transition. But as soon as we include adaptation and higher order both, then you have restoration of second order transition and you can get tiered synchronization. And this results which I have not shown, but that is also possible, and some results which are here in this publication, and I am here for the entire conference and be happy to talk about. And before I conclude, let me also show you one variation which is actually was challenging, and here we have this inertia term sitting here. So you can see here you have higher order interaction, but you have inertia term which is sitting here with theta I double dot, and this kind of equations are very important. This is the generalized chromato oscillator model, and this find their application in the power grid. So such kind of phase oscillator with inertia provide a very good solution for the very good model for the power grid. And now because of this higher order interaction and inertia, this Ottentenson approach becomes impossible to employ here. And recently I and now this Narayan, who is also here in the audience, he will present a poster here. We solved this thing using the self-consistency. Actually, he solved it. It was entirely his effort. He solved it using the self-consistency equation. So Ottentenson becomes quite difficult. So this is there also in the poster. With this, I think I have one concluding slide. So we have future direction, of course, are immense. So for all the results which I have shown, this is all to all. I have always writing down the mean field where the oscillator will see the mean coupling from the other oscillators. So as soon as you incorporate the real world networks, then writing down such kind of mean field, that itself becomes quite challenging. So that is the first thing, of course, and numerics also is very difficult to actually find first order transition if you have, instead of all-to-all coupling, if you take some real-world network, put some triangles, no, it's very difficult. In fact, Skardal and Aranas, they have shown in 2019 paper in Nature Communication, and we were not able to actually reproduce it so far because of the data perhaps they were using and we are using that may be different. There they have shown with the data that they have found first order transition, but since we may be using different data, we could not find. So that is the first challenge, which is to incorporate real world networks, do entire numerics. Even numerically also it's very difficult because how triangles are spread in the network, that is the challenging thing. And analytics, of course, you cannot have this odd intention or self-consistency, two different popular methods, becomes quite challenging. And there are of course few work, I think Dibakar Ghosh also keeps on publishing a lot on higher order interactions, so difficult to keep track, but I think he has done some work with the higher order interactions with real world kind of thing. And Skardal and Aranas also have published, but this is the real open thing right now. And second thing, which we have done a bit of effort, right now I have shown only two simplex, it means triangles. Now, is there any can be relation with the M simplex and M cluster? So that kind of thing, also the generalized one, we have shown that if we have triangles, then you can have cluster, two cluster, but such kind of, M simplex, M order parameters. So this is quite interesting because in real world system, you don't get global synchronization, you get cluster synchronization. So that I think is a very good future direction. And of course, inclusion of various other adaptive schemes. This is a more technical thing. I would like to acknowledge, of course, my this Sir Power Grant and Vajra project. And I have one announcement, just quick, one slide, that we have NetSci X 2025. That would be in India, in Indore. And that is a winter flagship conference of NetSci Society. With this, thank you so much.
Oh, yeah. Yeah.
Sarika, fascinating, but I think I just had a first transition to complete confusion here. You talk about various R's, right? Cluster, could you go to that slide? And then you say that you go from cluster synchrony to second order to first order. I just couldn't, I couldn't follow you there. I mean, could you explain like a high school kid, how do you do that? I mean, there are two R's also, right, in the equation?
Yeah, so this is the R which I said that I missed to define in that slide, but this is my generalized R. So if you have R1, that is the measure of global synchronization, because here M is equal to 1. So you get e to power I theta. So as you have e to power I theta, when all thetas are equal, you get R1 that is equal to 1. Now if you take R2, then you get e to power 2 I theta, and as soon as you have e to power 2 I theta, you can immediately see that two cluster synchronization is measured by R2. So R2 will be equal to 1 when you have two clusters which are synchronized.
Is that tiered synchrony as well?
Sorry?
Is that tiered synchrony as well?
No, so in tiered synchrony, everything was about R1. Though in the order parameter, this mean field, you get R2.
Exactly.
You get R2, but whatever I have plotted here, so you get R2 because you have two thetas A here. So when I write down the mean field, so here 2 thetas A, so K2 summation over 2 thetas A, that gives me R2, and one R1 which comes because of this theta K. So R2 is coming here, but whatever I have plotted here, that is entire thing is R1.
Could you just give us intuitive explanation of what is going on when you go from one type of transition to the other?
So, okay, maybe let me, so right now here you have K2, which is accounts for higher order interaction, that is quite small in the sense here. So K2 is smaller here for this particular model. I say K2 is equal to 2 is small. So as you are increasing pairwise interaction, you get here supercritical bifurcation and you get continuous transition. Okay, beta is equal to 0, beta is equal to 2, whatever beta value you take, you get very continuous synchronization because anyway K2 is very small. As you keep on increasing K2, you can see the effect of beta which is coming here. Okay, so for beta is equal to 0, no adaptation.